In this lecture, we discuss the Discrete Fourier Transform, or DFT. I will discuss the DFT differently than most textbooks, so I encourage you to read other resources to understand the mathematics behind the DFT. During our previous lecture on the DTFT, you may have noticed something that made you uncomfortable. The summation to create the DTFT goes from negative infinity to positive infinity. Since the goal of DSP is to compute signals digitally, we would need to sample x of n for all eternity before we could calculate the DTFT. And even if we had eternity and infinite storage, the DTFT is a continuous function, so we cannot store the DTFT digitally. So given these two problems, in many situations it is best to approximate the DTFT. Since we cannot always evaluate x of n for all eternity, we often need to truncate x of n to a finite number of samples, n. By truncating x of n, we will only be able to approximate the DTFT with a related function, the Discrete Fourier Transform, or DFT. Truncating, or also called windowing x of n, will cause many problems that we will discuss next time. We represent the DFT with a set of n samples. These samples are evenly spaced starting at 0 and ending just to the left of 2 pi, such that the frequency spacing between the last sample and 2 pi is the same as every other sample. We number these samples from 0 to n minus 1. The equation on the bottom left shows us how we represent the DFT mathematically. We evaluate x sub d of omega at 2 pi over n times m, where 2 pi over n is the spacing between our samples, and m is the index of our samples. As you can see, 2 pi over n times m simply replaces omega in the DTFT formula. We also change the limits of the summation to 0 to n minus 1. Because the DFT is not a continuous function, we change the integral in the inverse DTFT to a summation and change the limits to 0 to n minus 1 to create the inverse DFT. The nice thing about the DFT is that it still shares many of the same properties of the DTFT. For example, the magnitude of the DFT is still evenly symmetric, and the phase is oddly symmetric. This notation here is shorthand for the modulus operation. This equation then tells us that sample x sub 1 will equal sample x sub 12 minus 1, which equals x sub 11. And x sub 1 will also equal every n samples after that. In other words, x sub 11 plus 12, or x sub 23, and x sub 11 plus 24, which is equal to x sub 35. You do not need to understand the following equations right now, but keep them in mind. The DFT is a linear function, just like the DTFT. Parseval's theorem also still holds for the DFT. The time shift and modulation properties are also maintained in the DFT. The convolution of two signals is different when we use the DFT. Because x of n is periodic, the normal convolution formula performs cyclic convolution rather than linear convolution. We'll discuss the complications that result from cyclic convolution, as well as how to perform linear convolution when using the DFT later.